Hello, our topic is about the design of reinforced concrete column, and we will start with answering the following question. How to calculate the loads on the reinforced concrete column, and what are the different ways of calculating the loads on the column. The first one is the area method, and we'll go through that in details. We can look at the each column and determine the area which will give its load to that column. And there is another way of calculating the load on the column, and that's by calculating the reactions on the columns. In this here slide, we are talking about the area method, and as you can see here, uh, you have different areas about each column. The column in the corner, it's called, it has this area A1, and the column underneath it, it has the area A3, and this column A2, and this intermediate column has the area of A4. Now, how we determine this area? We look at the distance between the columns in this direction, and from half of the distance we can draw a line, and we say this width will be part of the area A1, and then we look at the other direction and we get a line in the middle of this distance, so we can say this part will be carried by area 1. So now we can create this rectangle. The same thing will apply for the column, and with the area A2, it has half of this distance, which is this part, and half of the x2, so x2 divided by half, and here that this distance, which will be L1, half of L1, so we can determine the area for the area A2. Now the load will include on this area the own weight of the floor slab, and that's very important item because it's heavy. The concrete slabs are heavy, and so now we can get the own weight of the concrete slab here, and the weight of the beams, the flooring material, what type of flooring you have. In different parts of the world they have granite and they have sand as a leveling material that will be heavy. So the flooring material, most of the time in Canada we have a carpet or we have hardwood, so it will be very light. We have to consider the flooring material, and underneath the ceiling we have mechanical, we have ventilation, we have chandelier, we have ceiling tile, so we can have the mechanical and electrical load on this area, and also the live load, which is the use of this area. And in residential areas we are talking about 2.4 kilonewton per meter square. Commercial it can be 2.4 or 3.6 kilonewton per meter square. In assembly areas we are talking about 4.8 kilonewton per meter square. So you can see here the area A2 and A4, and it will be very easy to calculate the area and the load on the column. Now when you calculate the load on the column for this floor, then you can multiply this load by the number of floors, and then you can get the total load at the ground floor level or at the first column. However, we have some restrictions or some notes about the live load, and also about the mechanical load, about the roof. So I'm just giving you an idea about how the concept is going to calculate the load on the column. The other one is using the reaction on the column, and in this way you can see that I have here that the area method on the right hand, on the left hand side. If you go to the right hand side, I took this example as for this column. If you calculate the load on the beam B1 and you calculate the reaction B1 to the left and B1 to the right, and you do the same thing for the beam B2, and you calculate the reaction B2 to the left and B2 to the right, and you have it for B3, and I looked at the beam from this direction that was on my right hand side. B3 are the reaction to the left, to the right, to the right, and the B3L the reaction to the left. Now the load on this column based on the reaction from the beams will be B1R plus B2L plus B3R. So that's this load per floor, and then if you can multiply that the number of floors, then you can get the total load on this, on the column at the base level. Now we have an example to have how to calculate the loads and design a column based on the load. So here in the floor and the floor below, the floor plan below, it's a 5-story building. So that's number one, 5-story, we know that. Commercial building, then we know we can evaluate the live load. Carpet will be used as flooring material, so we can estimate the weight of the carpet. And the ceiling tiles are regular commercial product. Now we want to design the column C4. This column, what we want to design, the spacing here 7 meter 8 7 7887999. So you have the everything what you need to design the column. Now our starting point is we wanted to calculate the load first, and then we can determine the cross section of the column and the reinforcing bars to make sure that this column can resist this load. And we want to make sure that it will be economical design, so it's not over design, and it should be safe. So we have a balance. We have also to look at the economical side of the design and also the environmental impact. We don't want to use too much material, and we want to use enough material for the project. So let's go and start to design this column. Our first step is calculating the load. Okay, so to calculate the load, we are going to use the area method. So the area for this column, I have 7 meter 8 9 and 9. So we start from this part, 7 meter divided by 2, this part, and here plus 8 meter divided by 2. So I have 3.5 plus 4, this here, that will be times this distance divided by 2, which will be 9 over 2, and we have this distance also is 9 meter, so I have 9 over 2. Now the total area which will be carried by this column will be 67.5 meters square. The live load for a commercial building, that's very common to have it 3.6 kilonewton per meter square. So we determined that from the beginning. Now let's look at the dead load. The dead load is the load which will remain in the building. It cannot go away. So the live load is the load which comes from the use of the building. The people can use the building, and it can fluctuate a little bit. So the slab weight, now with this thickness, we discussed before in another video about how to calculate the thickness of the slab, and so we estimated the thickness of the slab to be 0.3 meter. So the gamma of the concrete will be 24. So I have 7.2 kilonewton per meter square as a slab weight. Now the flooring weight, as because it's carpet, it's light, we assume that to be 0.2 kilonewton per meter square. Mechanical, ceiling, and lighting will be 0.3. That's a common number, 0.3 kilonewton per meter square. And the minimum partition load is 1 kilonewton per meter square. What's that? The Canadian code determine or require that we have to count for any partition to be built in any area of, in any location of the floor. The floor should be able to carry this load. So we have to add 1 kilonewton per meter square as a partition load. Now the total dead load will be 7.2. This here, the slab self weight, plus zero point 0.2 for the flooring, 0.3 for the mechanical, plus 1 is the partition load. So when we add that together, we get 8.7 kilonewton per meter square. The factored load per floor, now when we calculate our factored load, we have to count for some safety factor. So the factored load for the live load is 1.5. So I have 3.6 times 1.5 plus 8.7 times 1.25. We discussed that before. So it's 16.3 kilonewton per meter square. So I have the load per meter square. If I multiply this load times this area, so I can get the load per floor. So the total factored load per floor is 16.3. That's kilonewton per meter square. If I multiply that by the area, so I get 1098.6 kilonewton. Now the roof live load is assumed to be 2 kilonewton per meter square. So here we have some assumptions, and we have to look at the roof in details. But to make it easy for this example, we assume the load to be 2 kilonewton per meter square. It cannot be 3.6 kilonewton per meter square as this floor. I will speak about that soon, but let's now use the 2 kilonewton per meter square. So the factored load for the roof will be 2, which is this live load, times 1.5 plus 7.5 times 1.25. Here we removed the partition load. On the roof, you don't need to add the partition load. So that's important to notice. That 12.63 kilonewton per meter square. Again, multiply that by the area. I have 852.2 kilonewton. Now the total load of on the columns until the base, I have 4 floors. Now it's 5 floors. The top one will be the roof, which is this one. After that, I have 4 typical floors. 4 times 1098.6 plus the roof load. Now I know the load on my column at the base is 5246.5 kilonewton. Now my task will be how to design this column. Now for the design of the column, we have some items. Let's go before we we have the design concept. Uh, I have notes here, which is the accurate load on the roof. To we have to consider the snow load, and also we have to know if this roof is accessible or not. Can the people use it or not? So because that can determine the amount of the live load on it. Also, do we have green roof? If you have a green roof, then you have heavy load. The tree will be heavy, the dirt for the trees, and the people will go up to the roof and to enjoy the green roof. That means the live load will be changing. So now we have to know also the roofing material, such as we can have waterproofing, and we have a slope in the roof to make sure that it will drain itself. So the load for the roof is a special item by itself, and that our assumption for this roof load was easy. Just we are showing now the uh, intent of the design, how we design the roof in general. Now let's assume that I will have the concrete strength with 35 Newton per millimeter square. That's very important to assume that. And this strength of the concrete is a regular is a common one for the concrete. The width of the column to have 300 millimeter, and I spoke about that before, with the minimum to be 250. I wanted to 300 to provide 2 hours fire rating. So to estimate the length of the column in cross section, I have now the width is 300, and now what is the length of the cross section? I can neglect the steel reinforcement, and then I can have my calculation to get the length. So I can say the concrete resistance will be equal to the applied load. What is the concrete resistance? We have that before as alpha 1.8 and 0.65, that's phi c for the concrete, 35 f prime c, and that will be my cross section area. 300 the width, and L will be the length. So that should be equal to my applied load is 5246.5 times 1000 for the units. Now I can use a length of 960, and I find this length is too much. So and I still have to add my my reinforcing bars, and it will also contribute to the resistance of this of the column. So I tried now to have the length is 0.8 and not to have it as 900. So I went a little bit to optimize the length of the cross section. So 0.8, and then I assumed to have area steel is 4% from the area concrete. So that's to reduce the column area in the footprint. When you have a small column, then the people can use the area in a better way. So now I can estimate, now based on this ratio, I can estimate that I have my 14 number 25 bars. Now if you look at the PR maximum here, which will be alpha 1 times phi c times f prime c times area gross of the cross section minus the area of the steel, so that will be uh, in brackets plus phi s for the reinforcing bars times Fy times AST, the area of steel. So now 0.8 times 0.6 times 35, the area gross of the cross section 300 times 800 minus 14 bars, and each bar has a cross sectional area of 500. So that will be the net area of the concrete plus 0.85, that's phi s times 400 Fy for the steel bars times the area of the steel. So I got PRO here for this part is for the concrete, and this part is for which will be carried by the steel. I get at the end 6620.6 kilonewton. So PR maximum, what the column can carry based on the Canadian code, we can't take that 100%. We have to reduce this load a little bit and account for 80% of the PRO. So PR maximum here is 80% of the 600 from 6620.6. So I have 5296.5 kilonewton. This load here, which can be carried by this column, is bigger than 5246.5. It's a like almost there. It's just covered it. Normally you wanted to have a maybe 5% increase or 10% increase in the capacity. So that's this column might need to be increased a little bit, or you can increase the area of steel a little bit. But as what we have here, it's safe enough, but it's really economical for this column. And then you can have for the horizontal reinforcement, we assume to have number 10, and that will be at 300 millimeter. We have some video about the area of the reinforcement, and we have to add some intermediate ties between the to connect the bars, because we have 14 bars, and the maximum spacing between the vertical bars should not be more than 150 millimeter to make sure that the tie can support it. So when you calculate this distance, it's less than 150, so I need to add another tie in this direction. So the ties are important to provide more stability for the longitudinal bars. Now, talking about the ties, there are different requirements where you can add additional tie here. So this, as long when this distance is more than 150, then additional tie should be added. And here you can have this arrangement with enclosed tie like that, or you can have this arrangement with an hook like that. So when you have the distance is more than 150, you have different arrangement. Please refer to the Canadian code for this arrangement. Also, you can have for the column in general, you can have an I section or W section within the concrete, and that will be a composite column. Also here you can have reinforcing bars with also the steel members, and how they are going to construct the reinforcing bars of the column. So when you have the foundation like that, then you can have the dowels, and these steel bars are going up. For example, when we have 14 number 25, we have to get the dowels from the foundation going up, and then we can have the reinforcing bar with an overlapping length next to each other. And here in this part we have a steel, you have an anchor rods, and they are used here to have a base plate for structural steel column, and that was one of our project in the office. So that's here real life drawing or picture. And here you can continue and get your cage, or you can have the reinforcing bars, and you can see you can get embedded columns within the wall itself. Like as you can see here, you have the stirrups and different additional ties within the column. And here you have the dowels, the bars which are coming from one column, and another column will be placed above that. So you need to have an overlapping length between this bar and the additional reinforcing bars for the second level. Another thing which I would like to speak about is the top of the walls. So when you have here, that's the foundation wall at the end, but here we are adding a concrete beam, which is a precast, or if you have a steel beam, will sit on this pilaster, which is an embedded column within the wall. That's a pilaster. So now you have to consider the depth of the column of the beam, and then the top of the column will be adjusted to make sure that you have the top surface of the floor will be kept in accordance with the structural and architectural drawing.